Hello everybody! In the previous lecture, we have studied how to extract trajectories from videos capturing cellular movement. Today, I will present a method for analyzing and extracting useful information from macrophage trajectories. Specifically, I will demonstrate how to extract the diffusion behavior of macrophages during wound healing based on their trajectories. Trajectories are extracted using the algorithm described in the previous video. Here you can see the result. To study these trajectories, the first step is to smooth them. When macrophages move toward the wound, we distinguish their motion into two parts, drift and diffusion. While moving, they are attracted by the chemoattractant gradient. This is the drift part or the active part of motion. On the other side, the part of motion not related to the chemoattractant gradient is called the passive part or diffusion motion. Smoothing the trajectories allows us to distinguish between these two parts and study them separately. Consider a trajectory like the one shown in red on the slide. In the Lagrangian approach, the curve is discretized to a set of points and evolves according to a partial differential equation. Here, x indicates a point on the evolving curve. Specifically, the velocity is composed of three terms. The first is called the smoothing term. K is the curvature. This term will smooth the curve more when the curvature is high, for example, in the random parts. Since we want the curve to be smooth, but also as similar as possible to the original trajectory, we added a second term, called the attracting term. The attracting term can be defined in different ways, but the purpose is always to keep the evolving curve similar to the original. Finally, the last term in the velocity doesn't change the shape of the evolving curve, but redistributes the points on the curve, increasing the stability of the numerical computations. To define the attracting term, notice first of all that the trajectories are initially piecewise linear. This simply means that initially the curve is made of segments, which are the ones you can distinguish in the picture. To define the attracting term, we study the evolution of the lengths of the segments. Thanks to the formula you can see in the slide, we obtain the new length of a segment, and we can also recompute where its endpoints are on the evolving curve. So we find for every point on the evolving curve its correspondent point on the original curve. The attracting vector is then defined as the vector connecting two corresponding points. In this slide, you can see a video of the smoothing process. The curve in red is the original curve, while the blue curve is the evolving curve. As you can see, the passive part of motion, the random motion, are removed during the evolution, but the curve is kept as close as possible to the original. Applying the formula for the length of the segments, a segment can disappear. This occurs when the segment is in a region of high curvature, then in a random region. Thanks to the smoothing, we can also detect the random parts of the trajectories. Random part is defined as a region where more adjacent segments have disappeared. You can see in the picture the result of the algorithm. Once the random parts have been extracted, we can study their behavior as stochastic processes. The first thing we have to do is define what a stochastic process is. Imagine we want to model the movement of a particle for every second for, let's say, 3 seconds. At every step, the particle can go either left, right, up, or down with the same probability. It follows that it has a 25% probability to go right, 25% to go left, 25% to go up, and 25% to go down. Therefore, there are 3 time intervals, namely t equal 1, 2, and 3 seconds. And at every time interval, the particle will be in a position in space. We can describe it as a function of 2 variables, space and time. If we fix time, let's say t equal 1, we don't know where the particle will be at time t equal 2, but we know that it has a 25% probability to go either left, right, up, or down. In other terms, at a fixed time, the particle can be described as a random variable. As you can see, there are many possible trajectories the particle can take in this discrete grid. In this example, the number of possible trajectories the particle can take in 3 seconds is finite. Here you can see some examples. In the general case, the particle can go in every direction, thus with every possible angle. So the possible number of trajectories the particle can take is much higher, even infinite. The most common way to study the diffusion behavior of stochastic processes is to examine the mean square displacement. It is defined as follows. For each time interval, we consider the distance between points in that interval. For instance, if t equal 1, we examine the distance between the first and second points, the second and third points, and so forth. If t equal 2, we consider the distance between the first and third points, the second and fourth points, and so on. By considering the square distances, summing all of them, and dividing by the number of elements in the sum, we obtain the mean square displacement at that time. In this example, the initial time t0 is 1, and the final time, capital T, is 5. Once we obtain the mean square displacements for each trajectory and at each time, we consider the mean and plot them against time on a log-log scale and analyze the slope of the resulting line. Here you can see the result for 3 different datasets of macrophage data. If the slope is smaller than 1, the behavior is subdiffusive. If it equals 1, it is diffusive. If it falls between 1 and 2, it is superdiffusive. And if it equals 2, it's termed ballistic motion. As you can see, in our case, the motion of the random parts of the trajectories results in being subdiffusive. In this presentation, I showed you a workflow to analyze the diffusion behavior of macrophages. First of all, we smooth the trajectories. Then, we distinguish between active and passive parts of motion. And finally, we use the mean square displacements to distinguish the diffusion behavior of the passive parts.